As with my previous video, take everything I say in this video with a grain of salt. These are just my opinions, my theories, my guesses as to what I think is happening. This video in particular is a lot of guessing and assumptions because I don't really know what's happening, and these are some of the main concepts that I use to help me design frames and get them to perform the way I want them to perform. But I'm really just assuming a lot of things that may or may not be true. So yeah, please note that this is just my theories, my ideas, my concepts alone. It's really just food for thought. Also, I want to point out that Banggood has oddly allowed me to start making coupon codes for some products to get like 20-30 bucks off for a limited number of items being sold. So I'm putting these coupon codes in my description now, and they've also told me that they are allowing me to do giveaways directly from Banggood, which is great because I don't have to ship anything anywhere, and it's really easy for me to do that. And I've also asked them if I could just give away gift cards, and they said yes. So interesting. Let's see what happened there. Okay, so let's talk about props, thrust, and some concepts that I follow very closely based on a lot of backyard science, a lot of backyard testing. Again, these are just my ideas and theories, nothing more, just food for thought. Okay, so a prop. First, let's talk about what a prop looks like, or the thrust looks like coming off a prop on a bench test. So when this prop and motor is on a bench, first of all, when you look at bench test numbers, sometimes you see amp draws in the 50s or 60s or 70 amps drawn on 4S on a 5-inch prop at a 2306. I mean, that seems like a lot of amps, and it really is a lot of amps, but we don't see those amps in the air, and that's for a number of reasons, paramount of which is because the thrust coming off the prop can unload properly, and the whole quad is accelerating through the air and moving through the air. So there's wind, there's air that's being kind of drifted into the prop, and so the prop doesn't need to accelerate the air from zero. It's already getting air that's moving with respect to the velocity of the quad itself. So that's the idea, that the props and the thrust coming off the props kind of just unload, and the motor doesn't really need to work a whole lot harder to do what it needs to do. So in the air, you're going to see a lot more RPM because it's not a static environment, it's a dynamic environment. You're also going to see a whole lot fewer amps, but this is all heavily dependent on the prop selection, motor selection, your all-up weight, your battery, how things are functioning in there. There's a lot of factors that go into all this. But on a bench, the thrust coming off the disc is not going straight through. It's kind of like going in a circle. It's like vectoring around the prop. So you don't even get the prop, like the outer third of the prop doesn't even do anything because it's just circulating around the end of the prop. And it's not, bench tests are not a good test of props. Well, they are if you're looking for static thrust, but not with respect to overall thrust. They're a good test of motors, although they're really hard to read for motors, but they're definitely not a good test for props. I've asked people that do these bench tests to make like a wind tunnel so we can do some bench testing of props. It would be great, but yeah, nobody's done that yet. So the disc unloading concept that I came up with, and something that I really do follow very closely, is that if you have an arm underneath your thrust coming off the prop disc that's 30 millimeters wide versus an arm that's 5 millimeters wide, obviously the one that's 5 millimeters wide is going to obstruct the thrust much less than the one that's 30 millimeters wide. However, if the arm is 5 millimeters versus 4 millimeters wide, it's not really going to make all that much of a difference. The whole idea is that if the thrust cannot exit the prop and it's bumping into stuff and it's just being obstructed by things, the motor needs to work a lot harder to manage that prop, to get the thrust to change, to get the thrust to blow through. So in turn, it draws a lot more amps, and it's just not as effective in doing what it's trying to do, which means that you don't have as much control. The quad needs to expend a lot more energy getting this thrust to leave, just go, so it's not able to expend that energy on your inputs, on giving you the response that you want it to have. Now that's a very obvious concept. I took it a step further and looked at what's happening all over the prop. So I don't think that thrust comes off a prop directly in a column. Now I'm going to point out this blog Shredikit, which he hasn't been around for a while, but he's done some really, really cool testing of things. He has like a flow diagram which shows that the thrust coming off a prop, a racing quad prop in motion I'm going to say constant motion. I'll tell you why that's important in a minute. A quad that's in constant motion, the thrust going through the prop is actually very collimated. Yes, there's a little bit of a spiral on it, but for the most part, it's very collimated. It's not blowing out in a cone or any kind of just like vortex, cone shape, anything. It's just kind of going straight through the prop, which may or may not be true. I can't say yes or no. However, I do know that when you fly a quad that has prop guards, it sucks a lot more amps. Yes, there is a way to get slightly more thrust out of a prop duct, not a prop guard. However, on quads, in order to make that happen, you need to expend a lot more energy in the form of amps or volts or just watts to get that slightly more thrust out of that system. So it's not generally worth it on something like a multi-rotor. As far as I know, I haven't seen any evidence otherwise. So the fact that just having prop guards drastically reduces your flight time and increases your amp draw and reduces your control performance is telling me that there is at least some thrust going outwards from the prop. There is air being spun out from the side of the props. And if there's stuff around it, then that air bumps into stuff. It's not able to unload, and so the motor needs to work a lot harder to push that air through that duct system. And so, in turn, you have a lot less power available for control inputs and for the quad to execute your control inputs. Now, that's not just for prop ducts. That's just an extreme example. If I was to take tape and just tape the side of this quad entirely over, the air would bump into that wall of tape, so it would not be able to be as freely unloading as if there wasn't tape there, because I believe that there is thrust coming off the side of the prop disc as well. Now, the reason I said that the Shredikit diagram or model is a quad in constant motion and not acceleration is because in order to accelerate, you need to have a blast of power. So it needs to spin up, pull the air, push it down, and so you're getting a little bit, even if the air going through the prop is collimated, when you're accelerating, you blow air out sideways in a cone shape because it's just blasting down and going everywhere. It doesn't, it's impossible to me to believe that the air is coming through the prop disc and it's totally collimated. And so if you look again at that diagram, the diagram is, in a perfect world, a quad that's moving in perfect constant motion, not constantly accelerating. In the real world, there's actually drag. So you have to constantly accelerate just to keep a constant speed. I hope that made sense. I don't know if this model actually has drag built into it or not, but in my mind, I'm thinking that if there's drag, you need to be in constant acceleration or you'll be slowing down in order to maintain the same speed. So that concept alone tells me that while this diagram may be accurate, it may not be accurate when you factor in other things about the performance of these quads and what's happening. So this concept of disc unloading really does make at least the way I presented it and the way I think about it, which may be completely false, but it's the best explanation I have at this point, really does impact really significantly the way I build my quads. As I said, if you have your camera and your battery on the same level as your main plate with the props really close proximity, you will not have as freely unloading props or thrust coming off the props because it's just bumping into this solid mass of battery and camera right in the middle of the quad. And so in order to compensate for that, you need to have longer arms and a more spread out quad to give the props room to breathe, air to breathe. And so any interaction with any hard objects or other thrust coming off the discs or starving the back for air versus the front, any of that stuff impacts the amount of power needed for the quad to maintain its attitude in the air and reduces the amount of energy that the quad has to execute your maneuvers and your movements and your stick inputs. Next, let's talk about prop pitch and what happens when the pitch goes up or what happens when the prop weight goes up. So prop response and just the response of the quad in the air is something that I'm always looking for. And the way I personally set up my quads, or I want my quads to be, is I want the quad to be absolutely the most responsive thing it can be while giving me the speed and the rest of the performance that I want. But I dull my stick inputs tremendously. So the whole system feels ultra smooth to me. And somebody flew my quad the other day and they couldn't really tell the difference. They were kind of a little bit of a beginner, so it was hard for them to tell between quad and quad how things are different. But my quads are really squishy in the air. Like, I can just wobble the stick around and it doesn't really do all that much. My rates are stock and I just do an RC rate of 1.1 and everything else is default. But I do set my feed forward to somewhere between 6 and 8. Yes, a single digit, 6 and 8. I don't want a super, sharp, touchy quad. And so when the prop, first of all, if you look at the prop, you see how the prop kind of like thins out as it goes to the end. That's because the outer portion of the prop is spinning faster than the inner portion of the prop. And so as you spin up to speed, you want to take advantage of, or if you're not spinning really, really fast, you want to take advantage of this inner portion of the blade, because the motor will have an easier time spinning a short torque lever than it does a long torque lever. So if you put this aggressive point at the end, then it's going to be totally different. It's going to be a very aggressive prop. So props that have a really aggressive pitch, which this is supposedly a 2.6 pitch, but props that have a really aggressive pitch are harder to push through the air. They physically have more drag. It's harder to physically, it's like a paddle, pushing a paddle through the air. Props that have a more shallow pitch typically zip up to speed much quicker and easier. So if you have a prop that's shallower pitch but higher weight, then you have to overcome the inertia of the prop, and the motor needs to work hard to overcome that weight and needs to zip it up to speed in order to overcome that. Now, I don't know which one is more important, weight or the actual drag profile of the prop. I'm sure they go hand in hand. However, if you look at something like the HQ S3 blade, it's like a 3.5 gram blade, and the pitch on that thing is like 2.6. It's like actually 2 points, like almost nothing. And so the motor has the ability to spin that prop up and down really, really easily, because number one, it weighs very little, and the drag is very, very, very low. So typically, shallow pitch props have a better response. They should have a better response. Coupled with a low weight, they should have an exponentially better response, not just like twice as good response. It should get a whole lot better. Props that have a really steep pitch should typically have not as much of a response. Yes, once you're moving, they do generate more speed and they can generate more thrust. They do generate more thrust, but that's once you're moving. By the way, I have had somebody do bench testing between a steep pitch prop and a shallow pitch prop to try and find out if the steep pitch prop is actually stalling before it starts waving on the thrust, and I haven't been able to find any evidence of that at all, at least on a bench test. But as I said, static thrust bench tests are not a very good test for props, specifically props. Other things, sure, maybe for the most part, but even motors, it's really hard to read. But they're not very good for props. I wish there was a way for me to test this in the air, or just have time to figure out how I can test this in the air. But typically, more aggressive pitch props are not going to give you that immediate snap of power, that pop that you want in the quad. They will give you a lot more speed. However, the speed will kind of pour on. It's not going to give you a really super duper snappy quick response. Now there is one, well, steep pitch props typically weigh more as well, because there's a lot more material and the prop is usually more aggressive. And I'm not going to talk about the prop cord, or I'm not going to talk about anything more involving than that. But there is one unique area that there are very few props that fit into, and that is a prop that is extremely lightweight and extremely high pitch. Now, the one prop that comes to mind is the Dahl prop 5051, the Sean Taylor labeled prop. That prop is a 3.3 gram prop. It's one of the, if not the lightest 5-inch prop on the market, and it has a pitch of 5.1, which I don't know if it's actually 5.1. I just know it's really aggressive because it draws a lot of amps, and the blade is very, very skinny. And what's super unique about that prop is that it's incredibly light, so it does actually respond really incredibly fast, and the pitch is incredibly steep. So when it does respond and get up to speed, it pops really hard. So it's this like unique prop where it kind of overcomes its stalling in the air, because it is I mean, you could tell it's stalling because it takes more throttle to hover and less throttle to go fast. Whereas a shallow pitch prop is going to take less throttle to hover because it's more efficient at kind of pushing the air through the blade. And this is something I have actually tested against like some other shallow pitch props, just haven't talked about it. And the shallow pitch prop will not give you the top end of the very steep pitch prop. So there's a very, very, very interesting balance or imbalance of weight and aggression in that prop. However, you do pay for that performance in amps because it is very aggressive and it is very draggy to push through the air. So if you want a quad that is super responsive, first of all, you want to have the correct size motor for the prop. That means you don't want to have a 1408 or a 1507 motor running a 5-inch prop. You need to have a substantial size motor. I say the absolute minimum size for 5-inch is a 2207, and I would recommend up to a 2407 for 5-inch, but 2407 in my opinion is a little bit unnecessary because it is getting heavy and you're adding a lot of heft to your overall all-up weight, and that does drastically impact other aspects of performance. So I would recommend somewhere in the 2207, 2208, 2306 range, and really once you get past that, it starts getting a little bit different. Not bad, just different. And so when you want to step it up to 6-inch, then 2407, 2408 makes a lot of sense. Up to a 2508, I would say, at this point in time, based on a lot of the testing that I've done. Once you go up into 7-inch, 2508, I would say is the absolute minimum. But let's move on from there. There's another area of testing that Shredikit has done a lot of testing on, not a lot, well, at least one primary area of test, one type of testing, which is super interesting to me, and that is the drift factor of the quad. And if you have raced at all, then you know that as you're racing and you're trying to enter a gate, then exit the gate and go to another gate, if that other gate is like 90 degrees off axis or you have to actually make a turn, you typically turn before you enter the first gate so that you can make it to the next gate as fast as possible. And so it becomes a little tricky to line up your quad 50 feet before you enter the gate so that you can start turning to get to the next gate. And so that's the kind of drift that I'm talking about. The quad doesn't necessarily track entirely with the thrust that you're giving it. Now, the easiest, the most effective way to improve this drift or just have the quad grip and track exactly the way you want it to and have it just be a point and shoot quad is to drastically reduce the quad's weight with respect to its prop size. Disc loading. You want to improve your disc loading properties on the quad in order to get improved grip, and that really does work, as you can see, or as people have recently seen from toothpick class quads, which are really light and have really large props and have ridiculous numbers when you compare them to a 5-inch. They track unbelievably well. The grip is phenomenal in the air. So what Shredikit tried to do was put something called, or test something called side force generators. Now, I think his side force generators had an airfoil on them, but I don't know if that's actually going to help or make it worse. But what the side force generators were just vertical plates of carbon, and I'm using this quad because it's just easier because it's smaller, it fits on frame easier. It's just vertical plates of carbon underneath the props, such that it creates drag sideways. So if you look at this quad sideways, it's actually pretty aerodynamic from the side, so it can like slide through the air pretty easily sideways. If you were to add vertical plates to it, like a vertical plate like this, that would make it a lot less likely to slide through the air. Now, he says that he found in his blog, he found an improvement in the tracking of the quad with these side force generators. I'm not going to get into airfoils or any of that stuff, but I personally find it hard to believe that just a little bit of material or vertical plate underneath the motors is going to generate enough sideways drag to prevent the quad from sliding sideways through the air. And that's because as we are going through the air, you'd have to be going like 100 miles per hour for just like this much area to have enough drag to reduce the drifting and sliding through the air. So I actually don't think that effect is what's improving the issue. And there are various frames that have vertical plates in them, and a lot of people say that they do track better through the air, particularly frames by Carbix I think I said that correctly. And these guys are primarily from Sweden, and the guys in Sweden really love this frame concept and this frame design. I do have a couple of designs in this area. They are very unique. They are inspired by the Carbix, but really just the fact that they have vertical plates and there's a box is the only thing it's inspired by. It's a very unique structure that I've come up with. I haven't gotten around to testing it. Maybe one day I'll get around to testing it. The main reason why I haven't ventured into that area is because I'm a dumb American, and I'm too lazy to deal with things when they break. And replacing the arms on that kind of a quad frame is going to be much more involving than just swapping out an arm on one of my frames, which is a pretty quick, just 2 screws, pull it out, put it in, and go. And my concept of racing, or just anything, is that I need the thing to keep flying before I need it to really work and fly well and all that stuff. So number one for me is maintenance, and can I keep the thing flying? So that's why I really haven't ventured into that vertical plate or just more complex frame styles. And so what I think is actually happening is that the thrust, like I said earlier in this video, is not coming off the prop vertically. It's not just like straight thrust coming down. It's at least being spun into a circle, into a cylinder, if not a vortex or a cone coming off the whole prop, which is what I actually think is happening. What I think these vertical plates are doing is they're actually rectifying the thrust coming off the prop disc. So instead of the thrust being so spirally or spun around, it's actually becoming more straightened. And what that does is it helps the flight controller have a very 90-degree or right angle lever on the center of gravity on the quad, so that when it comes time to execute an input, it's not having to deal with this weird spun out thrust vectoring vortex that's coming off the prop disc. It has a more, not perfect, but a more vertical column of air to deal with. Does that actually obstruct the thrust and make it less efficient? Maybe. I don't know. That's a really hard thing to figure out. But I do think that would be my opinion as to why I think that might actually happen with those kinds of frames. Now, I haven't personally done enough testing in that department to say whether that is or is not true, but that's something that I might look into if I ever get around to it. I just don't have time to do any of this stuff anymore. So yeah, I hope that was really interesting and informational. I hope that opened some thoughts and ideas to you for when you're flying around and trying to figure out why your quad does the things that it does. And hopefully you start thinking about this stuff more, because I think about it all the time. I'm going to do a review on this quad in a minute right now. So floss your teeth. Take care. Bye-bye.